In this video, we will see one problem which is related to the laterally supported beam. Okay, a simply supported beam, laterally supported, laterally supported of span 10 meters, carries a UDL of 40 kilonewton per meter. Okay, in addition to the UDL, the beam is carrying a central point load 40 kilonewtons. Okay, one is the UDL load, another one is the point load. Okay. Design the section and check the section for shear. Okay, this two we have to do. Okay, design the section and check for the shear. First of all, what we have to do, we have to write all the given data here. Span of the simply supported beam, they have given L is equal to 10 meters. Okay, whereas effective length is also same, whereas K is equal to 1. Intensity of the load 40 kilonewton per meter. W is nothing but factored UDL is nothing but 1.5 into 10 into 40 kilonewtons, which is nothing but 60 kilonewton per meter. Central load also 40 kilonewtons and factors center concentrated load also 40 kilonewton. If you see factored concentrated load is the 1.5 into 40, which is nothing but 60 kilonewtons. Okay, here grade of the steel has been assumed as a Fe410 and most of the times we used to use Fi 250 Newton per mm square root. Okay, now we have to find bending moment and shear force. What is the factor bending moment for this one? M is nothing but WL square by 8 for simply supported condition with UDL, WL by 4 which is nothing but a point load with at center, which is acting at center. By using this, I have wrote here total load into length. Okay, for this condition I have written here total load. Okay, total bending moment I have calculated by using this one. By using factor loads, I found the total bending moment. Okay, if you here see, we can see the total bending moment which I got is 900 into 10 to the power of 6 Newton mm. After finding the bending moment, here if you see here, shear force occurs due to that particular load is nothing but, we can see for simply supported condition WL by 2. Okay, this is for shear with UDL, whereas W by 2 is nothing but shear with point load at center. By using these two equations, if you see here, and due to point load we can see shear force here 60 by 2. Total shear force will be 330 kilonewtons. This shear force has been considered without taking any self weight. Okay. After this, we can see here, depending on this moment, bending moment and shear force, here I am going to take a trial section depending on elastic modulus. Okay, elastic section modulus. Okay, elastic section modulus ZE is equal to M by Fy. Okay, from the using flexural equation, bending equation, we can see ZE is equal to M by Fy, whereas M is nothing but ultimate movement mu 900 into 10 to the power of 6 by Fy is nothing but 250. From here I can get the total elastic modulus will be 3600 into 10 to the power of 3 into mm cube. Okay, this is elastic section modulus. But to decide a section, okay, to decide a cross section, to take a cross section of the beam, I want to find plastic section modulus for that particular section. Here we have to find a required section modulus for particular beam. Here I am going to use I section. Okay, I section will have some shape factor. As for IS, they have given most of the sections having the I sections having the shape factor 1.1. I am going to use this shape factor to find the ZP value, whereas ZE is nothing but M by Fy. Here we can get, and S is nothing but 1.1. By using these two values, S and ZE values, here I have found plastic section modulus of the required section, ZP required. If you see here, shear factor S into ZE will give ZP required. And I got here we got 3960 into 10 to the power of 3 mm cube. This is the total required section modulus. But the section which is going to select, the trial section should have section modulus more than this one required value. Okay, I have gone through IS 800 2007 from the table number 46. I have chosen one section such that ZP value will be more than the 3960. And this value I have selected for the ISWB 600, which is having the ZP value 4341.63 into 10 to the power of 3 mm cube. This one I have selected. And the weight of the section is 1423. Okay, the section is having unit weight 1423 is the unit weight per meter weight length. This section is having the length. That section I have been chosen from there from in IS 800, and I have wrote properties of this section. See here, if you see here, these are the properties which are given in IS 800 table number 46. This is the area 140.36 into 1000 mm square. Area of the section, overall depth of the section H is 600, width of the flange 250, thickness of the flange 23.6, thickness of the web 11.8 mm, radius at the root. Okay, this is root is nothing but junction of the arc type of shape at the junction between flange and web portion of the I section or beam section, in beam section or any section we can take as R1 is equal to 18 mm, that is having the radius 18 mm. And depth of the web we can find like this: overall depth H minus 2 times to the thickness of the flange. We have to remove top flange thickness and bottom flange thickness, plus R1 is the nothing but root of the section, radius of the root. Okay, that radius will be present at the bottom flange, at the junction of bottom flange, and at the junction of top flange. By using this equation, I can find the total depth of the web. D is equal to 516.8 mm. Okay, for that particular section. And moment of inertia I have wrote here. This one is the moment of inertia, and elastic section modulus is also given in that particular table. Otherwise, we have to take this one from the IS handbook or steel table book. From there we can get the IZZ value as well as section modulus of the I section. After this, we have to find width of the outstanding leg, compression leg. Okay, total width of the flange we know here 250 mm, but outstanding leg from the junction of the web end flange to the outstanding edge of the beam, that one we have to find. Okay, that will be given from the BF by 2, and this BF by 2 will give 125 mm. And the B, if you see here in this section, B value will be the half of the flange width. This one we are using to classify the class of the section. Which type of section is that one we can classify by using this B value. Okay, before classifying this section, we have to find width of B to TF, width to thickness of the flange ratio we have to find, and this value should be less than 9.4 times to the epsilon, whereas epsilon is nothing but under root of 250 by Fy. Okay, which is nothing but 1. We can get here 1. And B by thickness of the flange ratio we can get 5.297, which is less than 9.4 epsilon. And D by thickness of the flange web we can get 516.8 by 11.8, where it is 43.797, which is less than 84 epsilon. These two satisfy the plastic section conditions. Hence the given section is the plastic section. We can decide the given section is plastic one. After deciding this one, we have to find design shear strength, whether design shear strength of the beam whether it is satisfying the conditions whether as they are given in IS 800, we have to check. Okay, how we can find design shear strength? By using earlier formula, we can calculate Fy into AWY formula we have to use, whereas the AWY is nothing but H into thickness of the web. H is equal to 600 into 11.8 is thickness of the web, into Fy is nothing but 250 mm by under root 3 into 1.5. From here we can get the design shear force as 929.009 kilonewtons, okay, which is more than the 330 kilonewtons. This is actual shear stress, which is less than the 929.009 kilonewtons. First criteria we have to check. For that purpose, what we have to do, we have to multiply this design shear force with the 0.6. Okay, when I multiply this 0.6, I got the value of 0.6 VD as 557.4054 kilonewtons, whereas 330 kilonewton is less than 557 kilonewtons. So, because of this reason, I am going to use MD formula as given in this one. Okay, plastic design moment of the trial section I can find by using this formula. MD is equal to beta B into ZP into Fy by gamma m naught. This one is the equation which we can use for V is less than or equal to 0.6 VD. This is the condition which we can use for this equation. Okay, MD we have to find like this, and it should be less than or equal to 1.2 into ZE Fy by gamma m naught. For simply supported beam, we have taken here simply supported beam only. Okay, for that case we have to check. Whereas MD we can find beta B for plastic section has given it as 1, and 4341.63 into 10 to the power of 3 is nothing but plastic section modules of the given section into 250 by 1.1 will be the Fy by gamma m naught. From here I can get the maximum moment capacity of the section or plastic design moment of the trial section as selected section is 986 kilonewton meter, which is more than the 900 kilonewton meter. Okay, from this what we can observe, the design capacity of the beam is more than the moment due to the applied load. Okay, factor load. Okay, hence the given section is safe in movement. We can decide this one as a section is safe in the movement, and we have to check whether it is less than this one or not. If you check with that one, this value is lesser than this one, whereas 1.2 into ZE Fy by gamma m naught will gives as 1051.148 kilonewton meters of moment, which is more than the MD. So we can say the section is safe for simply supported beam conditions. Okay. With this I am stopping this class here, lecture here. The next class we will see another problem or in the class.